Let's suppose that you are asked to do an optimization problem that's straight up algebraic in nature, very abstract. What is the point on this line, y minus 3x equals 7, that is closest to the origin? This is the type of problem that you're being asked to do. I'm actually going to level up and do a harder one. I'm going to ask myself, what is the point on the line a times y plus b times x equals c that is closest to the origin? So I'm doing a very generic version of this problem, right? Any a, any b, any c. I'm actually going to restrict myself to non-zero a's and ignore the case of vertical lines. Okay, now for the optimization part. Notice the word closest. That's the word you should be zooming in on. Closest means minimum distance. We are minimizing the distance. Between what? Between points on the line, that's the x comma y, and the origin, 0, 0. This, by thinking through that process, by telling yourself, what am I optimizing? Distance. Distance between what? These 2 points. What is the distance formula? All of a sudden, you've got something that you can try to take the derivative of and minimize. We're not quite there, though, because this thing has 2 letters in it. We need to get rid of the y. So what I'm going to do is I'm going to substitute y for a function of x. And I'm also going to tell you about a little tiny hack. You may know about this. But when you are minimizing or maximizing distance, as you will in this section a lot of times, you might as well minimize d squared instead, because you're going to find the same correct answer either way. And if you're minimizing d squared, no square root, right? Which means no crazy chain rule stuff. So it actually makes your life much, much easier. Very tiny change. So with those 2 changes, what I get is a function that I'm naming f. I get that f of x is x squared plus y squared, which is now c minus bx over a squared. This is the thing I'm going to minimize. A, b, and c are constants. X is a variable. So again, I'm assuming a is not 0 and that we're not doing any vertical lines. That's because a is in the denominator here. So by distributing everything and making it cute, I get a quadratic. I get 1 plus b squared over a squared x times x squared, right? That's the coefficient for the quadratic term. And then I get minus 2bc over a squared times x, that's my linear term, plus c squared over a squared for my constant term. I'm ready to take my derivative, which now that I've got my function arranged just so, it's really easy to do. I get 2 times that mess times x minus 2bc over a squared. That constant term falls away. So f is always defined because it's a quadratic, right? It's a parabola. So all I need to worry about is where the derivative is equal to 0. In fact, I happen to know that this thing is going to make like a right side up parabola shape, and that it's going to have a single crit, and that crit is going to be a minimum. So what I'm going to do here is take this derivative and set it equal to 0, and I'm going to solve for x. I get 2 times 1 plus b squared over a squared times x minus 2bc over a squared is equal to 0. I'm going to cancel those 2, so I'm going to divide by 2 on both sides. And what I'm going to get is that x is equal to bc over a squared all over 1 plus b squared over a squared. Okay, that's my x. I think I'm going to do a little work here to make it cuter. I don't like compound fractions, right? So I think if I multiply on both top and bottom by a squared, this guy gets a little bit cuter. Those little a squareds go away. And see how 1 times a squared is a squared? That's why he showed up there. That's my optimal x. It's unfortunate. Over the years, my feeling has always been that I'm annoyed at this point that I'm not done yet. Because I'm like, I found the x. What do you want? Well, the problem wants the point. The problem wants an x and a y. So you have to find a y. We're going to go back to this formula to do it. So when x is equal to this quantity, bc over a squared plus b squared, y is equal to c minus b times that all over a. Again, you can simplify. You can multiply top and bottom by a squared plus b squared and start canceling things. So I got a squared c plus b squared c minus b squared c all over a times a squared plus b squared. And so check it out. These 2, they cancel. And then 2 of the a's on top and bottom, they cancel after that. And what you're left with is ac over a squared plus b squared. So I have a point. I have an x, I have a y, I have 2 coordinates for my point. I'm done with this problem.